I said, do you have any questions? You said nothing.
No, I'm sorry. I was scrolling. I was finding
Oh,
the page because
you know what you need to do? You need to do this. You need to go, I have a question. Give me a second. I will answer it after we've done this. Cool? Okay. Are we ready? Okay, here we go.
How not to assemble a 100-piece jigsaw puzzle.
This is Mr. Colger.
Take all the single pieces in your hands, throw them all onto the table, and see if they'll form a finished puzzle. So why wouldn't this work? The chances that all 100 pieces would be lined up in just the correct way and fall into the right places is pretty well 0. So what does this have to do with chemistry? Well, how do we actually assemble jigsaw puzzles? We usually start with one piece and add other pieces to it one by one in a series of steps. This is similar to how all but very simple chemical reactions take place. Look at this chemical reaction. If this reaction took place in one single step, how many different particles would have to collide?
How many? No, you can do it. So how many reactant particles do we have? 23. So there would have to be 23 different particles colliding all at once, all with the correct geometry, okay, or orientation. Can you imagine the probability of that happening? 23 pieces all lined up correctly? Not likely.
The reactants include 5 of these, 2 of these, and 16 of these, which gives a total of 23 particles. If this reaction took place in one step, these 23 particles would have to collide in a single step. We can imagine 23 particles randomly moving in a container. The chances of 23 different particles colliding simultaneously and all having the correct energy and collision geometry is again about 0. So this reaction definitely does not take place in a single step. Even 3-particle collisions, like the collision of 2 hydrogen molecules with 1 oxygen molecule, are about 1,000 times less likely than 2-particle collisions, like a silver ion colliding with a chloride ion to form silver chloride. Most reactions that are not just 2-particle collisions take place in a series of simple steps, where each step depends on the others before it. The series or sequence of steps by which a reaction takes place is called a reaction mechanism. Here are a few points about reaction mechanisms. First, they cannot be determined simply by looking at the overall reaction. They are often deduced through much study and research, sometimes up to years. And don't worry, you will not be asked to come up with a mechanism from scratch.
So the research taking years, that's why I'm not a research scientist, because I'm not patient enough. I was doing, I went and did co-op jobs like in molecular biology and stuff like that, and nothing worked, and then it didn't work, and then it didn't work, and it was 8 months later, and I'm like, wow, this is not for me. I need something with more feedback right away. Like I just don't have the attention span. So hence, here I am teaching.
Just given a reaction. Some mechanisms are known, many are yet to be discovered. Maybe you'll play a role in discovering a mechanism someday.
I have had students go on and do this kind of thing, so that's kind of cool.
Now we'll have a look at a reaction mechanism that is known. Looking at this overall reaction and focusing on the reactants, we can see that there are 4 in 1 or 5 reactant particles. There's almost a 0% chance that these will collide simultaneously in the correct way to result in a one-step reaction. This reaction is known to take place in 3 relatively simple steps.
And in fact, at this point, I think we don't need to watch the video anymore. I think we can go to the notes that we have, because it pretty much goes through the same thing. Unless you're enjoying watching the video. Yes, do you want to watch the rest of it? Okay, let's do it then.
Step 1. An HBr and an O2 molecule collide and form an unstable activated complex.
Did you guys catch that? Watch the process. This is step 1.
And an O2 molecule collide.
What happened to the bonds? They broke. Yes, our covalent bonds broke. What do we have right now in between all the atoms? We have all these little dashed lines. What that means is we don't really know what's happening with the electrons at this point. This particular activated complex is so unstable. We've broken the old bonds, new bonds are in the process of forming, but we don't really exactly know where the electrons are. They're probably changing as we are speaking. Do you know what I mean? So we don't really know exactly what this species is like, but we usually just represent it as maybe something like this, or we could possibly write it as just HOOBr. Yes, we just take all of the reactant atoms and squash them together in one formula. So we have the HBr and the O2 is HOOBr, which we can call Huber. Okay, and that is our activated complex.
And form an unstable activated complex, which we call HOOBr.
Huber.
In some textbooks, activated complexes are called transition states. The two terms are synonymous. Bonds in an activated complex are often shown as dashed lines, and the formula is surrounded by square brackets. This bond now breaks, and these new bonds form. And now we have a new molecule called HOOBr. The bonding in the HOOBr molecule is significantly different than that in the unstable activated complex.
So what's the difference between this one and that one? Brackets, but like what's the actual difference between this and that? The bond formation. This one, the bonds are all like, ah! This one, we have definitely single bonds here, here, and here. Yes?
Even though the formulas for the two species are the same. The HOOBr molecule is much more stable than the HOOBr activated complex. We can summarize step 1 as HBr plus O2 gives HOOBr.
So you see how we have written, he's first of all got written the activated complex, then it becomes Huber, but normally we would just write a step of a reaction. We would not write the activated complex in the reaction. We would just leave it out. Yes?
In step 2, an HBr and an HOOBr molecule collide.
Oh, what just happened? They collided, and I'll show it to you again. Watch the lines.
In step 2,
Watch
an
the bonds.
HBr and an HOOBr molecule collide and form another.
What happened? Bonds broke and new bonds are starting to form, okay? Transition state, activated complex.
Your activated complex, which has 2 H's, 2 O's, and 2 Br's. So we call it H2O2Br2.
And you'll notice we just took all of the atoms in the reactants here and squashed them together into one formula. You could put them in a different order, it wouldn't matter, and that would be the formula of the activated complex. The activated complex is so unstable and we don't know what it looks like, so really writing a formula for it is almost like Yeah, you know what I mean? Okay.
These two bonds break, and these two new bonds form. And now we have two molecules of HOBr. We summarize step 2 as HBr plus HOOBr gives 2 HOBr.
So we have HBr plus Huber gives 2 Hober. All right?
In step 3, an HBr and an HOBr molecule collide and form an activated complex which has 2 H's, 1 O, and 2 Brs. So we'll call it H2OBr2.
Have you noticed how many particles are involved in each of these collisions? 2. And you have a question. You mean like if I flip this like this? If that happened, we would not end up with, oh, hang on, no. If that happened, we would not end up with product because that would be an incorrect orientation. Does that make sense? Because in order to get the next,
Which has 2 H's,
in order to get the
2
product
O's,
of this
and 2
step,
Brs. So we call it H2O2Br2.
so let's go till we can see the product of this step.
These two bonds break, and these two new.
So in order to get the HOBr and the HOBr, if this had been switched, you would have HOH and BROBr. Maybe, but then it's not going to go for this reaction, and then perhaps that step will go backwards. We do end up with reactions that go forwards and backwards, but it wouldn't contribute to this particular reaction. Okay? Yeah.
2 bonds form. And now we have collide and form an activated complex which has 2 H's, 1 O, and 2 Brs. So we'll call it H2OBr2. These two bonds now break, and these two new bonds form. And we're left with a molecule of H2O and a molecule of Br2. Both of these molecules are very stable. We write these as products in the equation for this step. We now summarize step 3 as HBr plus HOBr gives H2O plus Br2. We can now write a summary of all 3 steps. Step 1 is slow. How do we know that? Well, the relative rates of each of the steps has been determined experimentally. Step 2 is found to be fast, and step 3 is found to be very fast. We double step 3 to use up both HOBr molecules produced in step 2. Each step in a reaction mechanism.
Did you guys catch that? So we had step 1, 2, 3. Yes? Now if we look, step 1 is producing Huber. Huber is getting used up in the next step because we don't actually want Huber as a product. Okay? So Huber is getting used up in step 2, and we're making 2 Hobers. Now we don't want Hober as a product either. The only things we want as actual products are H2O and Br2. So the Hober is going to get used up in the next step. But because we have made 2 Hobers, how many times does this step have to take place? Twice. So we can just take that entire step and multiply by 2. Even though it looks like there will be 4 particles colliding, what's really happening is you just have 2 particles colliding once and another 2 particles colliding a second time. So that's what's going to happen here.
Found to be very fast. We double step 3 to use up both HOBr molecules produced in step 2. Each step in a reaction mechanism is called an elementary process. Let's focus on step 1 for a moment. Of course we see that it's slow. It means that the HOBr is being formed slowly. Looking at step 2, we see that step 2 needs the HOOBr made in step 1. So even though step 2 is fast, it depends on the slow supply of HOOBr from the slow step 1. It can only produce HOBr as fast as it receives HOOBr from step 1. So it doesn't produce HOBr very quickly.
If you're getting this, that's great. If you're not, we're going to go through this like slow fast thing in much more detail with like a little active participant demonstration. Okay, so don't worry if you're not getting this slow fast thing, okay?
And even though step 3 is very fast, it can't proceed any faster than the slow supply of HOBr from step 2 will allow. So if we wanted to speed up the rate of the overall reaction, which step would we have to speed up?
1, right? Because we cannot go any faster than the slowest step.
Step 1, step 2, or step 3? I think you can see that we would have to speed up the slowest step in order to speed up the overall reaction. In this mechanism, step 1 is the slow step. The slow step in any reaction mechanism limits or determines the rate of the overall reaction. Therefore, the slow step in a reaction mechanism is called the rate determining step.
Okay, and don't worry, all of this is in here somewhere. Okay, probably in a little box. So if you look on pages 83 and 85, what do you see in the little boxes? You see reaction mechanism defined. What is a reaction mechanism? Okay, so we know what a reaction mechanism is. What is an elementary process? Beautiful. And reaction intermediate we'll talk about in a moment. And then on page 85, what is the rate determining step? The slowest step in a reaction mechanism. So usually if you find something in a box, it's going to be like a definition or an important sort of concept. Whoa, what happened?
In this video, we're going to focus on reaction mechanisms.
No,
How
go
to write
back.
the rate law.
Not that I dislike Organic Chem Tutor. Organic Chem Tutor is amazing.
How not to assemble a 100-piece jigsaw puzzle.
Yeah.
Gives. Let's focus on step 1. So if we wanted to see that step in any reaction mechanism limits or determines the rate of the overall reaction.
So therefore it is
Therefore,
called
the slow
the
step in a reaction mechanism
Beautiful.
is called the rate determining step. I think you can see that if we had a way of speeding up only step 2, which is already fast, or only step 3, which is already very fast, that speeding up neither of these could speed up the overall reaction. Everything depends on the product from the slow step, so the only way to speed up the overall reaction is to speed up the rate determining step, or the slowest step in the mechanism. Just a little point here. In this mechanism, the slow step is step 1, but that's not true in every mechanism. In some mechanisms, the rate determining step is step 2, or step 3, etc. But what is always true is you must speed up the rate determining step in order to speed up the overall reaction.
Now, just going back for half a second, let's take a look at our mechanism here. Okay, what could we do to speed up this reaction mechanism? I want you to think of some factor that we could change. We could add a catalyst. Yes, we could. We could increase the temperature. They're both gases. We could squish it. Yes, we could squish it, decrease the volume, and thereby increase the pressure. What else could we do? We could increase the temperature. We could also increase the concentration of what? The HBr and or the O2. Okay, would it make any difference if I happen to have a jar of HOBr and I threw some extra stuff in there? No, even though you can't really do that because it's not a very stable substance, okay? All right, let's go back here. There we go.
Always true is you must speed up the rate determining step in order to speed up the overall reaction. If we're given the steps in a reaction mechanism, we can use them to write the equation for the overall reaction. We use this mechanism as an example. Before we add up all the reactions, we circle the species that we can cancel out. That is, identical species that appear on both sides of the arrow.
Okay, so you guys on page 81, you guys are going to circle, actually at the very bottom of page 83, sorry, not 81, the very bottom of page 83, you are going to circle the species that you can cancel out. Give it a try, bottom of page 83. Circle anything that appear on both sides of the arrow. All right, let's see how it goes. We've all tried. We'll find out if we're correct.
Arrows. We see that HOOBr is on the right of step 1 and on the left of step 2, so we circle it. We can also circle the 2 molecules of HOBr that appear on both sides. And now we draw a line under the last step. We write the words overall reaction here. We add up all the species remaining on the left side of the arrow.
Why don't you try and do that at the bottom of page 83? I know that the 83 is going to get in the way, but it's sort of where the arrow is. Why don't you try adding it up and leaving out the things that you've circled on both sides? And when you're done, you can check your answer on the next page. And we'll let Mr. Colger tell us about it as well.
And write them here. There is 1, 2, and 2 more, which is a total of 4 HBr molecules. So we write 4 HBr molecules here in the overall reaction. And there is 1 molecule of O2 remaining on the left side, so we add it here in the overall reaction. Now we add up all the species remaining on the right side of the arrows and write them here. We have 2 molecules of H2O, so we write 2 H2O here. And we have 2 molecules of Br2, so we write Br2 here. Every time we write a new equation, we always check to see that it's balanced.
Is it balanced? Yeah, it should be. If you've managed to cancel out everything correctly, it should work out. Okay, but you always check just in case you've made a boo-boo.
We have 4 H's on the left side and 4 H's on the right side. We have 2 O's on the left side and 2 O's on the right side. 4 Brs on the left side, and 2 times 2 equals 4 Brs on the right side. So the equation is balanced. Now, here's one for you to try. Pause the video and write the equation for the overall reaction. Then resume to check your answer.
Okay, so this is, oh, you know what? Have I written this anywhere? I don't think I have. Just write it on a little piece of paper for yourself. Okay, you don't have to write down the question if you don't want to, but you can. If you need paper, it's at the back. I'll have to redo this thing so it's got that little doodad in there. So you're wanting to circle the things that are on both sides, cancel them out, and then add up the reaction, the steps to give you the overall reaction. All right, when you're done, give me a little wave. Okay, so we're mostly done. I'll give you another minute or so if you're not quite done yet. Check with your partner if you've finished. Make sure you get the same thing.
Circle the AX2 on both sides. Circle the AX on both sides. Circle the X on both sides.
We had something new. Yes? Here we produced some AX2 and then we used it up. Here we produced some AX and then we used it up. But what happened with the X? We added it in and then it came back out. So they're different, okay? And we'll talk about more about that in a moment.
Now we have two A's and two X's on the left side of the arrows. So we write those in our reactants. And we have A2 and X2 on the right side of the arrows. So we write these in as the products. We check now to make sure the equation for the overall reaction is balanced. We have two A's on both sides and two X's on both sides. So the overall reaction is written and balanced.
Okay, now just to go back here, when something is produced in one step and then used up in a later step, that is called a reaction intermediate. Okay, so that's a reaction intermediate. Who are the reaction intermediates? Something that gets produced in one step and then used up in a later step. Who are the reaction intermediates in this reaction? AX2 because it's being produced and then used up. AX is also getting produced in step 2 and then used up in a later step, step 3. Is X following that same pattern? No. And it turns out that X, something that is used up and then produced, that is a catalyst. Okay? So if it's If it gets used up and then made again, it's a catalyst. Because remember, catalysts do not get used up in a chemical reaction. Do you remember the matchmaker? Comes along, grabs person A, grabs person B, puts them together. Then they can go off and grab a different person A, person B, put them together. So the catalyst is not getting used up. It goes in one step, but it comes out in the next step, and it can then go on and catalyze other instances of that same reaction. Okay. Let us go then here. There we go. So we've been here, la 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 la, la 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 la. Okay. A reaction intermediate, oh, in fact, that's in, is a substance which is produced in one step and then used up in a subsequent or later step. And it doesn't have to be the step right afterwards. You could make it in step one. This is page 83. You could make it in step one and use it in step two. You could make it in step one and use it in step three. It doesn't matter as long as it gets used up again somewhere later. Okay? You could make it in step two and have it used up in step four, whatever. All right? Now on page 84, we've now learned about reaction intermediates and activated complexes, and sometimes people get the two of them confused. A reaction intermediate only ever occurs in a reaction mechanism, whereas activated complexes occur in single step reactions and multi-step reactions. Okay? The reaction intermediate is the product, quote unquote, because it's not really a product, in one of the steps, and then it's used as a reactant in a later step. A reaction mechanism is written in the reaction What? That should say a reaction intermediate. Intermediate is written in the reaction mechanism equations. This is page 84. Whew. Yeah, that sentence made no sense before. Now, an activated complex, and you should know this definition, it is short-lived. Is it high or low potential energy? High. And it is unstable. Quite frankly, all those three things mean the same, but you might as well say them all. And it is an arrangement of atoms that occurs when reactant molecules collide and bonds are broken. It can either then form new bonds to become the final product or a reaction intermediate, or it could actually go back and become reactant again. Sometimes that happens. Sometimes you have particles collide, all the bonds break, and then they're like, no, I'm going to go back to being reactants again. But we're going to mostly ignore that and just say it collides, the bonds break, old bonds break, and then new bonds form, and it becomes either the final product or the reaction intermediate. It is not written in the reaction mechanism equation. So the activated complex is not written in the mechanism equations. So let's take a look at this Huber-Hober reaction. And we are representing the activated complex with an asterisk. Okay? Step one has an activated complex. And where does it occur? It occurs in the arrow. Do you remember how when we were watching and we had the bracket HOOBR, that, and it was sort of like in between? So that's where it is, and so we don't actually write it. We don't write the activated complex in the equation. But reactants intermediates do occur, right? So we've got our reaction intermediates here, 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 here. Whereas our activated complex, we don't actually write it, it's just in the arrow. As that step proceeds, we get an activated complex. If you have a 3-step reaction, how many activated complexes will you have? A 3-step reaction, a 3-step mechanism will have 3 activated complexes. One for every arrow. And remember, if you need to write the formula of an activated complex, just mash all the atoms of the reactant particles together into one formula. The order of the atoms does not matter. So if we had a, just to illustrate that, if we had these, HOOBR and HBr as our reactants, we could write our activated complex as any of these, and nobody's going to care. Kolger put a bracket around it. I've also seen them put with a star beside them. Both of those are fine. Do I think you're going to have to write the formula for an activated complex on either one of my exams or on the AP exam? No, I do not. But just in case, you can just smash them all together, okay? And this is actually from Hebden, all right? And they've shown our activated complex there, just so you know, you saw it in the video. There it is, blah, blah, blah. Reaction intermediates are more stable than the activated complex. Does that make sense? Yes, because you've actually formed bonds, and bond formation means you're going to a lower potential energy. Yes? Therefore, the activated complex will have a higher potential energy than the reaction intermediates. Rate determining step, we already talked about that. We're going to do the dishwashing demo just to make sure that that comes home to. I need 3 volunteers, please.
Yeah.
All right, I got 1 there. I got 2 Alvin, and I got 3 RN. Try to put people from all over the room. Now, come on up to the front and just stand alone here. We'll close this off so you don't get blinded by it. Okay, here we go. Okay, now we're going to do the situation where we have a very slow first step. So RN is a perfectionist, and she is the dishwasher. Okay, so you're going to, with every dish that you get, you are going to scrub it and make sure that every little bit of gunk and grime is off of it. Then you are going to pass it to Idemar, who feels like he's getting paid minimum wage, the waiters aren't sharing your tips, And so he's just gonna like, be done with it, okay? And so you are going to rinse and dry this thing, okay? So you just be like rinse, dry, and then you're gonna pass it to Alvin, and Alvin is going to go put it away, and you're again a disgruntled employee, so you're just gonna be like, ah, and so just put it down, right there, okay? All right, so RN, our employee, okay, the other two disgruntled employees. All right, here we go. Take more time, RN, you're not doing a very good job. Inspect it, make sure it's all good. Like really, really take your time with it. Yeah? You guys are just sitting around doing nothing while we're waiting for. All right. All right. Now we're gonna swap roles a little bit. Now, you are a disgruntled employee, so you're just basically gonna dip that thing in the water and send it along. Okay. Idamar, you are still a disgruntled employee. All right. And Alvin, you have to go and you have to put those on the other side of the room because that's where they go away. Okay? So here we go. Are we ready? Here we go. No, this one. Let's wait till it's done. There we go.
Okay.
No, you can't take one until you get
Wait,
one.
what? Okay. Can I toss it to him or no? Can I toss it to him or no?
No. So even though steps 1 and 2 are fast, we cannot go any faster than step 3. Do we want to do step 2 as a slow step? Yeah. Just for argument's sake. Okay. Alvin, you can come back. And we're finally going to have Idamar is now our star employee of the month. Disgruntled employee. Okay, so you're going to make sure that you have rinsed it off. So you're going to rinse it, and then you're going to dry it. Take your time, shake it off, right? Make sure it's all dry. Okay. And Alvin, you're just going to put them right there. Okay, here we go. Alright, I'm not doing enough job. There's still stuff on here. And what are we calling Idamar? Use the rate determining step. Can you guess which of these has the highest activation energy? Think about that while they're doing this. Who has right now the highest activation energy? Idamar has the highest activation energy. Okay, are we good? Excellent. Thank you guys so much. You were wonderful volunteers. Love that. Thank you. Thank you. Here's another little illustration, just if you want to see it kind of visually. Your rate determining step, you can't go faster than the smallest funnel if you're pouring it through. Otherwise, it'll just overflow. Yeah? Uh-huh. Yeah, right? Now, in any reaction mechanism, the rate determining step is labeled slow. All the other steps are labeled fast. So how many slow steps will there be? One. Only one step is slow, all the rest are fast. So if we gave you this reaction mechanism, what would step 3 be? Step 3 would be fast. Could you please find the overall reaction? And you know that you have this in your book, so you can look at it in your book if you want to as well, right? This is page 86. Now this one's kind of fun because we have 2 Cl being produced in step 1. One of them gets used up in step 2, and one of them gets used up in step 3. What do we call Cl? It's called a reaction intermediate. Do we have any other reaction intermediates? What else? CCl3 is another reaction intermediate. And so our overall reaction then would be, who are our reactants? Cl2 plus CHCl3 goes to HCl plus CCl4. Excellent. And so the products of the overall reaction are the HCl plus CCl4. I don't know why I asked that twice. It's kind of stupid given that we wrote the overall reaction. Write the formula of the activated complex for step 2. Yes. Yes. Yep. Because how you write it doesn't matter because we don't really know what it's doing. Yeah? So yeah, what could we write for the activated complex for step 2? Give it a try. Compare what you wrote with what your partner wrote. That would be good. What else? Cl, CH, Cl3, or anything else. Stick an asterisk on it, or stick brackets around it, or do both. Yes? Okay. And then we have the solution. Huzzah. Find the missing step of a mechanism. Now, this is a little bit trickier. This is our overall reaction here. And we want to know what step 3 is. Now, usually when you're given a question like this, you will be given the overall reaction at the top. And then you'll be given the steps and told what step, what goes in the third step. So what I would advise that you do is that you take these three and you draw a line under your three steps, because when I like to add downward. So I like to have my final reaction 2A 4 plus B plus goes to 2A 3 plus B 3 plus. Did you want to try it, or do you want me to do it for you? Give it a try, see how it goes. Give it a try, see how it goes. See if you can find step 3. When you're done, check with your partner, see if you got the same thing. Okay, if you had any difficulty whatsoever, I will show you a method that tends to work very well. First, what you do is you go through and you cancel out any intermediates or catalysts that cancel out within the steps you already have. So you can say, I've got a C3 here, and I've got a C3 here, and those cancel out, which is good, because do I want those in my final reaction? No. Now I say, what do I have in the steps that I want in the overall? I have 2A4s and I want 2A4s. I have 2A3s and I want 2A3s. Now what I don't have a B plus. Yes? I want to have a B plus on the left-hand side, so I'm going to have to put a B plus on the left-hand side. I want a B3 plus on the right-hand side, so I'm going to have to put a B3 plus on the right-hand side. So that takes care of everything that I want. The other thing you have to ask yourself is, if I haven't canceled anything that needs canceling, I need to cancel it. I need to cancel C2 plus, which means it has to go over here, C2 plus. And I also need to cancel C4 plus. And that means that my step 3 is B plus C4 plus gives B 3 plus C 2 plus. Okay. Let's take a look at page 89. We're going to combine what you read last night, potential energy diagrams, with reaction mechanisms, and we're going to look at catalysts. Okay? So page 89. Okay, I meant to highlight that and I just scribbled on. Never mind, it's okay. Each step of a reaction mechanism has its own activated complex. So if you have 3 steps, you'll have 3 activated complexes. How many peaks will you have in a potential energy diagram? 3 peaks, because each peak represents an activated complex. Each peak is where we find an activated complex. The higher the peak is from the original energy, the higher the peak from the original energy, that's going to be the slower the step. The activation energy for the overall reaction, and I don't know, I assume that at some point you've seen EA to mean activation energy. We had that somewhere? Yes, of course. So the activation energy of the overall reaction is going to be the difference between the highest peak, the potential energy of the highest peak, and the potential energy of the reactants. This is going to make a lot more sense when you see it on a picture, but we're just going through this. The slowest step, the highest peak from the original energy, is the rate determining step. It is the slow step. So the slowest step, the rate determining step, is the highest peak. Delta H doesn't matter. Do you remember delta H is a state function? So it doesn't matter whether you do a reaction in 1 step or whether you do it in 3 steps. The initial and the final remain the same, and so delta H remains the same. If a collision has enough energy to get over the highest peak, it will have enough energy to get over all the other peaks as well. Does that make sense? Think about that. If a collision has enough energy to get over the highest peak, it will have enough energy to get over all the other peaks as well. And it doesn't matter whether the highest peak is number 1 or 2 or whatever. So let's take a look at this diagram here. What kind of a reaction is this, endothermic or exothermic? That is exothermic. Delta H is positive or negative? Negative, all right. And if a ball, let's say we're bowling, yes? If I bowl and that ball can make it to the top of the first hill, it's going to pick up kinetic energy as it goes down, and then it'll lose kinetic energy as it goes up, but it won't lose all of it, because how much kinetic energy did it have? It had enough to get to the top of that hill, right? So it'll have enough, it'll gain some of that kinetic energy back so it can get to the top of this hill, and it's going to be like, woo! So even though this looks like it's a bigger peak, it doesn't matter, because it picks up all this extra kinetic energy so it can get to the top of that final peak. Does that make sense? Pretend there's no friction, right? Yeah. If there was friction, this would be like all be a mess, but you know, we're going to be a frictionless state. It's an analogy, it's not perfection. Yes? So even though the ball goes very far down into that second valley, it will pick up a lot of kinetic energy, and it will, in the process of going down that second hill. Okay, here's our activated complexes on the diagram. So this is our Huber-Hober reaction. This is on our next page. Huber is the first intermediate. So where do we find intermediates? Reaction intermediates are found in the dips, in the valleys. Activated complexes are at the peaks. Reaction intermediates are in the valleys. Whoops, why did that go small? Yep. How to recognize a reaction intermediate? I know we've just said this. It appears first in the products, and then it appears second in the reactants. And we spoke a little earlier about a catalyst. And while we're here, how about you define, if you can, I don't know if you've seen one yet, define catalyst to your partner as well as you can. I don't know if you've seen a good definition yet. Yes. Okay, so a good definition of a catalyst, you'll notice, what does it say over here? The definition needs both parts. So if you are asked to define a catalyst, you need to say that it is a substance that speeds up a reaction by providing an alternate pathway or mechanism for the reaction with a lower activation energy. Or you could just say a lower activation energy pathway, right? That would make it like more concise. Yes. Yeah, there would be different steps, okay? So it provides a new mechanism with a lower activation energy. And you should also mention that the catalyst is not used up in the reaction. Alvin, yes? No, you can say lowers the activation energy, but you should also say by providing an alternate pathway. Okay? Especially if you're taking AP, because AP is all over that providing an alternate pathway. How to recognize the catalyst. This is not a definition, so you're not going to be like, oh, a catalyst is something that appears first in the reactants and then later in the products. That is not a definition. That is how you recognize it. But you'll say, oh, here we have our catalyst. That's different from a reaction mechanism, because where do reaction mechanisms appear first? They appear first in the products and then in the reactants. So a catalyst first in the reactant, then in the product. So you can see reaction intermediate, first on the right, then on the left. Catalyst, first on the left, then on the right. The reaction intermediate is used up as the reaction proceeds. The catalyst is not used up as the reaction proceeds. So what I'm going to have you do for homework is page 88. And also, and that includes the questions from Hebden listed at the bottom. And I'll throw something else up there. Pages 76 pages 76 to 79. There we go. Hi. Yes.
Just curious. So, first one, we've got the series of steps, the measures.
Yes.
You said that they can be found experimentally. But if they're super unstable, only there for a second, how do we know that the bit that happens in the arrow, how do we know that it's shaped up?
We don't. That's why we like put a star beside it or brackets around it. We're like, this is kind of like what it might be, right? Yeah.
Second one, the framework talks about inhibitors instead of catalysts. How does that work?
Usually what will happen is you'll have these two things that want to react, and the inhibitor will just be really good at binding to one of them. It gets in the way.
So it's not something like.
So in theory, you know, if it's not a very good inhibitor, if it knocks into it hard enough, it could knock off the inhibitor and then.
The good inhibitor just locks onto one of the two reactants. Thank you.
Hi.
What book is for the 76 to 70?
Oh, this is also
It's
same book.
one, and it's like just reading, right?
It's work.
Oh, okay.
These are questions.
Okay, yeah.
Okay, and regular kinetics workbook.
And earlier, I kind of missed the YouTube person who said like why certain like elementary process is fast and certain one is slow. Like I forgot what.
It'll just have to do with the nature of the reactants.
Oh, okay.
Yeah, you don't need to explain it.
Okay, I got
Some of them are fast, some of them are slow. You'll never, as a grade 12 student, be able to tell me which one is which without being told.
Okay.
Okay?
Yeah, I just wondered why.
Yeah, no, you won't be expected to tell me which is the fast and slow step unless I give you, if I say this step is slow, you're like, oh, all the rest are fast.
Yeah, okay.
Or if I'm like, these two steps are slow, what's that step? Or this step is slow, that step is fast, the other one has to be fast because you can only ever have one slow
Oh, it's
step.
just because of their nature.
Yeah, yeah. Yeah.
PE, right?
Yes.
Then it says temperature is a measure of average kinetic energy. And
Yes.
it's saying like potential energy won't be affected by it just moving faster.
Uh-huh.
But it says if it's a measure of average kinetic energy, mv squared, right? So wouldn't it be moving faster, increase the average kinetic energy?
Yes.
And therefore,
It doesn't change the potential energy contained in it, though.
oh, okay.
Right?
Okay.
I can make this hamburger move faster, but it still contains the same number of calories.
But wouldn't the total energy increase though? The kinetic energy increase?
Yeah, but you're putting in energy from outside the system. That the total energy of the universe is not changing, but you're putting in energy from the system.
So
yes.
So the potential energy doesn't change.
No.
It's only cause kinetic energy increases. Okay.
That's right. Yep. Yep.
Our monster question.